Hi everyone, welcome to PrepFusion. So let's learn the real analog electronics, the way PYQ should have been solved and the way it should have been studied. Let's study in the same manner. Okay. So we are going to solve the amazing PYQs, amazing 10 PYQs we are going to solve. And I would say that just by looking at the question, don't skip it. Let's just say, sir, I have already solved this particular problem. So should I skip it? No. Please watch it completely. You would surely get to learn something new here. Right? Like here I am teaching all the concept as well, that this is NMOS, this is PMOS, which one is drain, which one is source, how the current would flow. How do we define drain source? Why do we call, like, why do we say that MOS is symmetric structure? Why drain and source are interchangeable? Everything I am explaining. That's why the video is longer, right? Then same based on that we are solving the problem. This question you would have already seen. There people would say that there is a negative feedback, so the gain would be A upon 1 plus A beta. Beta value is 1. But what is the actual explanation? How you are making this MOS into this particular op-amp? What is the meaning of phase shift? Why this is positive terminal? Why this V1 was positive terminal? Why this V2 is negative terminal? All these things I am explaining using the MOS circuitry and op-amp. I am comparing both of them. Then this question has been explained. So you would see that in all the questions you are getting something good. This question has been already explained on YouTube, but here I have given a different approach. Okay, a different approach is there, that using the concept of Fourier series, how you would be solving it. Okay, using the concept of Fourier series, like what is there, like here why the DC value will be 0, if DC value is 0, how the current would be 0. So are you able to understand the point that in each question you will be getting something different, something surely different you would be there. This question you might have solved with RCLN 1 plus beta upon 1 minus beta, but that thing we are not doing here. We are actually understanding the meaning of what is the meaning of non-inverting Schmitt trigger, what is the meaning of inverting Schmitt trigger, how we are getting these characteristics, and based on that characteristics how we can solve this problem. Simple RC circuit, no formula approach, zero formula, pure concept. Okay, pure concept. If you have a basic idea of analog electronics, you would be able to understand this particular video. Okay, and then like here I am recommending other videos as well, that what all videos you can watch. This video also have been explained, but here I have given more concept, that how you would have solved it with respect to frequency domain analysis. People say that minus SRC and then simply they would differentiate this particular thing. That is wrong, absolutely wrong. Why it is wrong? How you would have understood with the frequency domain analysis. So all these things I have explained here. A very different approach you are going to get, and I am recommending some videos as well, that these videos you can watch. So we will get started with this video now. Okay, and all the concept I have taken into action, like oscillator I have taken, op-amp I have taken, MOS amplifier I have taken, DC analysis of MOS I have taken, diode circuit I have taken. So all the concept also I have taken, clipper, clamper, not clipper, clamper, but rectifier, all these circuits, everything has been taken in those 10 amazing PYQs. So it would be roughly around I guess 2 hours of video, or more than 2 hours of video. Then in these 2 hours, after these 2 hours, you will feel like that I am a complete different person in analog electronics. So surely watch it, and let's keep up some target. What target we are keeping up? We are keeping up a target of 5k views. 5k views in 2 days. Okay, 5k. Once you watch this video, you will realize that why I am keeping this target. 5k views in 2 days and 250 likes. This is the target we are keeping up. Along with that, surely the most important thing is comments. Once you are done watching this video, you need to comment down. Sir, what did I feel? If you have already studied analog from somewhere else, did you feel something different here? Are you a better person in analog now? Are you a much more comfortable person in analog now or not? Okay, so you are going to comment that. So let's get started. Let's get started with now analog electronics in a different way. Let's get started with the first question now. Yeah, let's see this question now. So we will come to this question, but let's see some concept first. So first I am going to ask you some questions. Look at these circuits, 1, 2, 3, 4, 4 circuits you need to look, and you need to let me know which one is NMOS and which one is PMOS. Sir, where there is a bubble, where this bubble is there, that is sir PMOS. And sir, where there is no bubble, sir, that is NMOS. Sir, where the arrow is outside, arrow is looking outside, so this will be your NMOS. And sir, if the arrow is inside, sir, this will be my PMOS. So finding which is PMOS, which is NMOS, that is not difficult. Now I ask you, which one is source and which one is drain in case of NMOS and PMOS? So I am asking about this particular circuit. Let me know which one is source, which one is drain. So a lot of people would say that, sir, where there is an arrow, sir, this will be source, and sir, this will be drain. And sir, in case of PMOS as well, sir, where there is an arrow, that would be source and this would be drain. This is absolutely wrong, absolutely baseless. This is true only for the AC analysis. Okay, only when we do the small signal analysis, then only it is true, but not for the large DC analysis. So this statement that saying that this would be source, this would be drain, that is wrong. Why is that so? Because have you seen the MOS circuitry, MOS schematic have you seen? Like as a device, this is how the MOS would look like. If I need to make it NMOS, then this would be N plus, this is N plus, and this will be your P substrate. The middle one will be gate. This is known as gate. That's for sure. There is no doubt about it. The middle one. Here the middle one, this will be gate. There is no doubt about it. This is your gate. But now you see this schematic. Isn't it symmetric? Isn't it symmetric around the gate? Whatever that you see here, the same you see here as well. Isn't it symmetric? Like if someone says that, sir, this is drain. Someone would say that, sir, right hand side is drain. And sir, left hand side is source. Then he is looking from front. What if someone is looking from the back? Someone is looking from the back. For him, what will be the right side? This will be the right side. Then he will say, sir, this will be drain, this will be source. Isn't it symmetric? Symmetric around the gate potential. It is symmetric here, no? So how you can define one is source, one is drain? So that's why using the physics, that physics can be explained in the comprehensive course. But here, after studying all the physics, what we conclude that in case of NMOS, the one which is at higher potential, that would be known as drain, and the one which is at lower potential, that would be known as source. And in case of PMOS, the one which is at higher potential, that would be known as source, and the one which is at lower potential, that would be known as drain. Now if someone give you this particular circuit and they ask you which one is source, which one is drain, then you need to ask, sir, which one is at higher potential, which one is at lower potential. Now if I say this is at 3 volt and this is at 5 volt, then you will say that, sir, I can see one thing, that, sir, this is NMOS because arrow is outside. Sir, this is NMOS. In case of NMOS, I know that the one which is at higher potential, that would be drain. You need to remember only one thing. Rest all you would be able to tell. NMOS, higher potential, drain. Then lower potential will be source. In PMOS, simply opposite would be there. So, sir, this is a NMOS, arrow is outside. The one which is at higher potential, that would be drain. And, sir, this will be source. And if I just interchange it, or if I simply put 7 volt here, then because of the arrow, this will be source. No, the one which is at higher potential, that would be drain. This would be drain. And this would be source. And what will be the current direction? You let me know what will be the current direction. Current direction is always from, someone would say that, sir, in case of NMOS, it is from this point to this point. Nothing like that. Current direction is always from the higher potential to lower potential. Higher potential to lower potential. That's it. Current direction is always from higher potential to lower potential. So which one is at higher potential, which one is at lower potential? You let me know. This one is at higher potential, this is at lower potential. So this will be the direction of current. If I randomly make, sir, this is 3 volt, this is 5 volt. I am not asking which is source, drain, nothing. Just let me know what will be the current direction. Higher potential to lower potential. Current will always be from higher potential to low potential. Okay. So I hope all these concepts are clear to you. I know a lot of misconceptions are there. People blindly put up anything that this is source, this is drain. Higher potential source in case of PMOS, and lower potential drain in case of PMOS. And in case of NMOS, higher potential will be drain and lower potential will be source. Same goes here as well. Here there is no arrow, then how will you determine? People blindly say that this will be drain, this will be source. No, this is how we don't determine. We determine one which is at higher potential, that will be drain, and the lower potential will be source in case of NMOS. Understandable? So let's go to this particular circuitry. Although it is already mentioned that it is NMOS, it is PMOS, although it is already mentioned, even if it was not mentioned, we would have got to know that there is no bubble, NMOS, bubble, PMOS. Now initially, what is the scenario? This is at 5 volt. Now this capacitor is uncharged, right? It would be somewhere, it would be written that those capacitors are initially discharged. That means zero charge is there. So V1 would be 0 initially. So initially the scenario is, look, this gate is just a controlling eye. This is controlling. Okay, this is just a controlling eye. So we don't care about this potential as much. But as of now, we care about these two potentials. This one is at 5 volt and this one is at 0 initially. 5 and 0. So which one is drain, which one is source? This is a NMOS. This would be drain and this would be source. What will be the direction of current flow? Current will always be flowing from higher potential to lower potential. So this will be the direction of current flow. Let's go to PMOS. This is 5. This is 5. This is at minus 5 volt. I don't care about it actually. This is at plus 5 volt. This was at plus 5 volt. This is at minus 5 volt. Now initially this is also discharged. 0 potential it is having. This is also discharged. That means this is also having 0 potential. Which one will be source? Which one will be drain? This one will be source. Why is that so? The one which is at higher potential, that will be source in case of PMOS, and this one will be drain. And the current will always flow from higher potential to lower potential. Say yes or no. Now, what is the current flow? How would you determine the current flow? In case of NMOS, if you guys know, if your gate to source potential VGS, VGS is greater than the threshold voltage, then the current would keep on flowing. Then current will not be zero. And in case of PMOS, if your VSG is greater than mode of VT, VSG, source to gate potential, this potential, gate to source, source to gate, if that is greater than mode of VT, then ID will not be equals to 0. So did you understand the current flow? When the current will keep on flowing, if your VGS is greater than VT, then current will keep on flowing. And here if your VSG, source to gate potential, because here this is a higher potential, no? So higher to lower, like we don't care about the gate potential actually, but this is at higher potential. So VSG I am writing, and here source is at lower potential. So here I am writing down VGS. So this is the condition. If VGS is greater than VT, then ID would not be equal to 0. If VSG is greater than mode of VT, then ID would not be equal to 0. Here, what is the threshold voltage given? Sir, for both of the cases, VTN for NMOS and mode of VTP for PMOS, in both of the cases, the value is given as 1 volt. So let's see initial scenario in this particular case. In this particular case, what is happening? For the first case, this is sir 5 volt, this is 5 volt, this is 0 volt. So this one is drain, this one is gate, and this one is source. So what is the value of gate to source potential? So that is 5 volt. Is it greater than VT? Absolutely, it is greater than VT. So if VGS is greater than VT, then what will happen? Current will flow. What will be the direction of current flow? The direction of current flow will be this. Current will always flow from higher potential to lower potential. So the direction of current flow will be like this. So that current will be flowing through the capacitor as well. Like in the MOS, the current will be flowing like this. Higher potential to lower potential. The same current will go in the capacitor as well. So what will happen? The capacitor will start charging. So capacitor will start developing the charge. So from 0 volt, it will start developing the charge. Let's just say it has developed some 2 volt. So if it has developed 2 volt, then what is the value of VGS now? This is 2 volt, this is 5 volt. So value of VGS is 3 volt. Is it greater than 1? Yes, sir. That means more current will flow. So current will keep on flowing. Yes, more current will flow. Now let's just say it has developed 4 volt. So this is 5, this is 5, this is 5, this is 4. It has developed 4 volt now. Now what is the value of VGS? 5 minus 4, that is 1 volt. Is it greater than 1 volt? No. That means now the current flow would stop. Is that understandable to you? Here the current flow would stop. That means it can charge up to 4 volt only. This 5 volt wanted to charge it to 5 volt. But it did not happen. This 5 volt has the capacity to charge it to 5 volt only. But it did not happen. Why it did not happen? Because VGS should be greater than VT. Then only the current would flow. No, VGS has to be greater than VT. Then only the current would flow. But what really happened? Now the gate to source potential has become 1 volt. Now the current cannot flow. So it will stop at 1 volt. Sorry, it will stop at 4 volt. So what will be the steady state value here? V1 steady state value will be 4 volt. Now a lot of people would mug up the answer. Sir, it would be, answer would be VG minus VT. A lot of people mug it up. So 5 minus VT value is 1. So answer will be 4 volt. They will click on this option and luckily they got it correct. But what if I do one change? What change I am doing? In place of 5 volt, I have put 3 volt. Then what you would say? Sir, answer would be 5 minus 1, 4 volt. So answer would be 4 volt. Wrong. Why it is wrong? Because what is the applied potential here? 3 volt. You tried to charge this capacitor, but how it can go above 3 volt? Like this is one of the condition of turning on the MOS. Other condition is also there, that drain to source potential should also be greater than 0. Drain to source potential should also be greater than 0. Now just as you have applied 3 volt here, now what will happen? The source will, this potential will start going up. So let's just say it has reached to 3 volt. It has reached to 3 volt. From 3 to, if it tries to go to 3.1, then what will happen? The potential difference between them would become negative. And if it is becoming negative, what will happen? Current will not flow. Basically, there is a source of 3 volt only. How you can get more than 3 volt here? This 3 volt is charging this capacitor. Like there is a RC circuit. Okay, here I have applied 5 volt. This is RC. What is the maximum voltage this capacitor can get? 5 volt. The charging source is 5 volt only, no? So how it can get more than 5 volt, right? So similar scenario is there. Now in the examination, this has been already asked in the gate examination. There they have put 5. But in the examination, if they want to make some change, what they would do? Because people would mug up this answer, Vg minus Vt 4 volt they would put. It will not even reach the 4 volt. First, it needs to reach to the 4 volt, no? So don't mug up the answer. Have some concept, okay? Have the concept clear, how the concept goes. That sir, first I would see this particular circuitry. I would know that higher, this is NMOS, higher potential, drain, source, gate. Now what will happen? Current would flow. This will start charging. My condition is that VGS should be greater than VT. Along with that, my drain to source potential should also be greater than 0. This is 5 volt. It has the capacity to charge till 5 volt. This is 5 volt. It has the capacity to charge till 5 volt. But will I reach 5 volt? That would be determined by this particular guy. So he says that my VGS value should be greater than 1. That means you can reach up to 4 volt only. So what will be my answer? Answer will be 4 volt. Okay. So I hope you have understood. What about this one? So 4 volt, this could also be the answer, no? So let's see what answer would be correct. Now let's go to the second one. This condition. Sir, what kind of circuit it is? PMOS. In case of PMOS, the one which is at higher potential, that will be source. This will be drain. Sir, surely this will be gate. So what all are the condition is there, sir? Condition is VSG should be greater than 0 and VSG should be greater than VT. Sorry guys, VSG should be greater than mod of VT. This is the condition for the current to be non-zero. Along with that, the source to drain potential, or forget about this condition. Let's not talk about this particular condition, VSD. But as of now, the condition is that VSG should be greater than mod of VT. What is your source potential? What is your source potential? So that is 5 volt. What is your gate potential? That is minus 5 volt. What is your VSG? 10 volt. Is it greater than VT? What is mod of VT? That is 1. Yes, sir. If it is greater than VT, then the current would flow. Current would flow. Current would flow in the capacitor. The current would flow in this direction. See the direction of current flow. Higher potential to lower potential. In the capacitor, it would flow in this direction. That means charge will be developed in this direction. Now, till what point it may charge? Sir, let's just say it has charged to 4 volt. So what? Will it turn off? The MOS will never turn off, no. Here drain potential is changing. Drain potential will never decide whether the MOS will be on or off, whether the current will be non-zero or 0. This particular thing will decide. No, VSG is greater than mod of VT. So no matter how much voltage is developed, this MOS, this potential difference, VSG, that is 10 volt. This is not changing. But here what was the scenario? This was 5 minus V1. So this V1 was changing, that's why this potential was changing. So here there was a problem that it may turn off. But here it will always be on. This is 5, this is minus 5, it will always be on. And now what will happen is that it will keep on charging. It will keep on charging till what potential? Who is charging? This 5 volt is charging. So it can charge up to 5 volt. There you go. So what will be the steady state value of drain? That would be 5 volt. So this answer is wrong. Is that understandable to you? Is the difference between NMOS and PMOS is clear to you? In PMOS, the scenario is that VSG should be greater than VT. Yes, I am taking this scenario. Already it is greater than VT only. 10 volt is always greater than VT. Now no matter whatever the voltage your capacitor is developing, it will always be greater than 10 volt. That means my MOS will always be on. If it is always on, it will always keep on charging and it will charge up to 5 volt. But sir, in this case, NMOS, what is the scenario is that, sir, I wanted it to charge to up to 5 volt, but what really happened? After 4 volt, it is not able to charge. Why is that so? Because sir, VSG now has become 1 volt. Because of that, the MOS is off. Now it will be able to charge up to 4 volt only. There you go. This is the complete scenario of a pass transistor logic. This is known as pass transistor logic. In brief, I have explained the whole concept, but detailed concept could be given in the comprehensive course. Okay, and a lot of questions we have solved. Here also we have connected some capacitor. Although in the gate examination, this kind of question have not been asked yet. But what we can do is that here also we can connect the capacitor. Now here interesting thing would take place. So that kind of things we can consider in comprehensive course. But whatever that has been asked in the gate examination, that we can solve. Right. So I hope this question is clear to you. Let's go to the next one. The same kind of question in gate examination only in 2014. You should be able to solve it. Have some patience and try doing it. Just let me tell you one thing. Wherever there is nothing connected, you can always take capacitor. Okay. You can always consider capacitor here. You can always consider capacitor here. Now just think about it, have some patience and let me know what should be the answer. All are NMOS. What is the condition, sir? VSG should be greater than VT. Which one is drain, which one is source? Can you tell? Sir, this is at 5 volt. What does that mean? Sir, this will be drain. Now let's analyze only the first state. What will happen? Sir, it will try to charge. Right? Only in the first stage, this will be drain, sir, this will be source. Only I am analyzing this first stage. This first stage I am analyzing. This is 5 volt. So this will try to charge, but up to what potential it can charge? Up to 4 volt only. Because if it tries to go above 4 volt, then what will happen? VGS, not VSG, sorry guys, VGS. This is your gate. This I am talking about NMOS, no? So VGS should be greater than VT. So gate to source potential should be greater than VT. 5 minus 4, that is 1. What is the value of VT given? That is also given 1. So VGS should be greater than 1 volt. So it can charge up to 4 volt only, sir. If it tries to go above 4 volt, then what will happen? MOS will turn off. So now it has been charged up to 4 volt. So first stage we have analyzed. After analyzing the first stage, this is something that we have got to know, that this has charged up to 4 volt. Now what about the second stage? In second stage, sir, this has been charged up to 4 volt. Right? And here you analyze now. This is at 4 volt. For the second stage I am talking about. For the second stage I am talking about. This is at 4 volt. This is at 5 volt. And now this is at 0 potential. This Q node. This is at 0 potential. So this will be drain and this will be source. Again the current flow would take place. Till what point it will charge? It will charge up to 4 volt only. Why is that so? First thing is that, sir, there is 4 volt, so it will try to charge up to 4 volt. And will the gate allow it? Yes, gate will say that until VGS is greater than VT, I am allowing it. So gate is saying until VGS is greater than VT, until this condition you are satisfying, I am allowing it. That means he will allow it to charge up to 4 volt as well. So whatever the potential was put up here, the same potential has been put up here as well. Now let's analyze the last state. Last state, again the same. This is 5 volt, this is 4 volt. There you go. So what this capacitor will say? Sir, I will try to charge up to 4 volt. I will try to charge up to 4 volt, but I need to ask gate. Are you allowing me? Gate will say, yes, I am allowing you. Until your VGS is greater than VT, I am allowing you. So he is allowing till 4 volt. So 4 volt is also allowed. So 4 volt, 4 volt, 4 volt. That means what will be the steady state value? At PQR, the steady state potential are 4 volt, 4 volt and 4 volt. That's it. Is that understandable to you? This came in 2014, then this came in 2022. So the concept of past transistor logic is completely clear to you. And this kind of questions, if they are coming in the examination, you would be able to solve it. No matter whether it is PMOS or NMOS, whatever it is. Okay. Let's go to the next one. Let's see this question. Again, we will come to this question, but I will ask you something and then we will come back to this particular problem. Okay. So have you seen this kind of circuitry in your life? Yes, sir. This is op-amp. Let's say I call this as V1 and this as V2. And it is having a finite gain of A. And this is your V0. So what your V0 can be written as? V0 can be written as, sir, gain A multiply with V1 minus V2. This is positive, this is negative. Now just let me know one thing. If V1 is increasing, if V1 increases, then what will happen? This value will also increase. Right? If this value increases, then multiply with gain A, this V0 will also increase. It is pretty obvious, no? V2 is fixed, I am not changing V2, I am increasing V1. If V1 increases, V0 increases. Is that understandable to you? Yes, sir. Now let's do another thing. I keep V1 as fixed, now V2 increases. If V2 increases, then what will happen? If this particular thing increases, then this total thing would decrease. If V2 increases, then this total thing would decrease. If this total thing is decreasing, then what will happen? V0 will also decrease. So if positive terminal, this positive terminal is known as non-inverting terminal. What name I said? Non-inverting terminal. Non-inverting terminal. So if non-inverting terminal increases, then what will happen? V0 increases. And if inverting terminal increases, then what will happen? V0 decrease. So if this increases, V0 increases. If this increases, V0 increases. And if this increases, then V0 decreases. Is that clear to you? Very simple thing. Now let's go to this particular circuitry. And before going to this particular circuitry, do you know all these things? That if I make a simple NMOS, okay, and now I say that here I am increasing the gate potential, then what will happen to source potential? Sorry, what will happen to drain potential? You are not saying anything about the source potential. I am just saying that source is grounded. Let's just say source is grounded. So if you increase the gate potential, what will happen at the drain potential? Do you remember the gain? It would be minus GM R naught. Gain is negative, no? Like V naught by V in. Let's just say this is your V in and this is your V naught. So V naught by V in would come out to be minus GM R naught. That means this is how we can say. So if V in increases, you would say that sir V naught is increasing only but in the negative direction. So actually it is decreasing. So if V in increases, this will decrease. In the common source configuration, if gate potential increases, drain decreases. Another one. This is your gate, this is your source, and drain is grounded this time. If this guy increases from here to here, what gain you would get? Sir, I don't know what gain I get. I nearly get gain equals to 1 only, or it is equals to GM R naught upon 1 plus GM R naught. But sir, here there is no phase shift. There is no 180-degree phase shift. There is no negative sign here. So if I increase V in, then my V naught will also increase. That means if this node increases, then this node will increase. Let's see the last one where your gate is grounded now. This guy is grounded. Now I apply the potential here and I talk about here. So here also, sir, I know that sir gain would come out to be, let's just say here there is RD connected. So gain would come out to be sir GMRD. Again there is no negative sign. What does that mean? That means sir if I increase this potential, if I increase this particular potential, then this potential will increase. So these three diagrams should be absolutely clear to you. You will not remember sir this is common source, common drain, nothing. If source increases, then drain would decrease in this configuration. If you are increasing the potential at source, drain would decrease. In rest of them, nothing would, like no inversion would be there. So that means if gate increases, then source would increase. You need to know that from where you are starting. You cannot say that sir if source increases, then gate will also increase. No. If gate increases, then source will increase. If source increases, this is your source, this is your drain. If source increases, then drain will also increase. If this potential increases, then this potential will also increase. Understandable? Let's go to this particular circuitry. If I say if V1 increases, from here to here I am going, from here to here I am going. So if I just make a circuitry, if I just make one circuitry so that you guys can remember it. So if you go from here to here, what is the phase shift? 180-degree phase shift. When you go from here to here, what is the phase shift? 0 degree. And you go from here to here, what is the phase shift? 0 degree. Will you be able to remember this diagram? Just I am putting this in a box so that you guys remember it. That will you guys be able to remember this diagram? If this potential increases, this will decrease. If this increases, then this will also increase. If this increases, then this will also increase. Is the diagram clear to you? So if this potential increases, then this potential will also increase. Now if this potential increases, then this potential will also increase. Say yes or no. If this potential increases, this potential increases. If this increases, then this will also increase. So what you are learning from here is that, sir, if my V1 increases, then my V naught is increasing. Okay. Now second, what about V2? Sir, if V2 increases, where is V naught? This is your V naught. From here to here, how much is the phase shift? 180 degree. So sir, if V2 increases, this will decrease. So sir, if V2 increases, then V naught will decrease. Now if I replace this particular circuitry, something like this. Where one node is positive, one node is negative, and this is your V node. Let me know which one will be V1, which one will be V2. So this will be V1 and this will be V2. Say yes or no. This is the same question now. Let's define this node as V2. And let's define this node as V1. If this node increases, then this node will increase. If this node is increasing, then this node will increase. What does that mean? V1 is positive. It might happen that both are positive as well. It is not necessary that sir one will be positive, other one would be negative. No, it is not necessary. You have to check. If this guy increases, then what will happen? This guy will decrease. What does that mean? That means V2 is negative. This V2 is negative. So I can replace this particular circuitry with whatever that is there above. I don't care. I just got to know that I can replace this now somewhat like this. Plus minus. This is your V1, this is your V2. Now what they have said is that open loop gain is 40. What is the meaning of open loop gain? That means they are giving this value. This value is 40. Like when this output was not connected back to this V2, at that time the gain was 40. This is the condition that they have given. Now what they did, they connected this output back to input. This is how they have connected it. Now this is the scenario that you are getting. So what you need to find out? You need to find out V out by V in, because V1 is V in now. V1 is V in now. You need to find out V out by V in now. So what will be your V out by V in? So this V0 can come here, right? V0 is directly coming back. This has been connected to V2. So V0 has become V2. So sir, V in minus V0 into 40 would be equals to V0. So 40 V in would be equals to 41 V0. So what will be the value of V0 by V in here? 40 by 41. There you go. So answer is option A. A lot of people did it correct in the examination. What they said that is that, and a lot of educators have also given the solution. Nowhere I saw this particular solution. That is actually the correct solution. They have just said that it is in negative feedback. Why it is in negative feedback? No one explains. Okay. Since it is in negative feedback, A upon 1 plus A beta, sir, beta value is 1. Why beta value is 1? How it is a feedback? How it is a op-amp? So are you able to understand now? Are you able to appreciate this particular thing? That this is how this particular question was framed. Although this is a standard way, like this is a standard circuitry, it is known as OTA. Okay, I teach it in my comprehensive course, and this is actually the first stage of op-amp. We always make the IC, but what is there inside the IC? This is the first stage. Then other stages would also come. So this is the first stage of the op-amp. Normal op-amp, one stage op-amp, this is how it would be made. So although those comprehensive thing I am not going to teach, but this is how you can understand it, that this kind of question was asked in the examination. In my own channel, in my own channel, Himanshu Agrawal, in 2022, I have posted this question, that I am replacing this circuit with this particular circuit. One node is positive, one node is negative. Which one will be V1, which one will be V2? It has been posted on my channel in 2022. This question came in 2024. They have asked the same thing. It's just that they connected back and they asked the gain. So if you know this particular thing, if you know till this point, then surely you would be able to solve this particular question as well. Okay. So same goes for our test series as well. We have conducted Killer X, although Killer X is private now. Booster X we are going to conduct, although it will be easy. Concept X we have conducted, or our Fusion test series also you can see. There I frame tougher problems. It's not that I am blindly making it tough. I have seen the PYQs. Based on those PYQs only, I think that what kind of questions can be framed. And based on that, I make those test series. People would say it is tough, but when these kind of questions would come in the examination, either they will see some irrelevant solution or they will mess it up. Okay. So yeah, that was the second question. Let's take another question now. Let's take this one. This is also a very, very good problem. Already have been solved by me on YouTube, but here I will give you a different solution. Whatever that has been given on YouTube, that I will not give. Some different solution I will give. So figure shows a half wave rectifier. It is a half wave rectifier or not, I don't care. Okay. The diode is ideal. You need to find out that. Just read this line. Average steady state current through the diode, that you need to find out. So diode current is ID. So first you need to go to the steady state. Now at the steady state, whatever that you get, then you need to take its average. Let's just say diode current is somewhat like this, and somewhat like this. Diode current is somewhat like this. This is the graph of diode current. So what do I need to do? I need to see the steady state. At steady state, I am getting this square wave. Now I need to take its average. So this average I need to take. This is what they are asking. Is that understandable to you? Okay. Now can you let me know what is your diode current equals to? So diode current is equals to the current in the resistor plus the current in the capacitor. So your diode current is equals to the current in the ID I am putting. Okay. diode current is equals to IR plus IC. Now at the average, can I take the average like this? Yes sir. In signal system we have studied that if two functions are in addition, you can surely take the average like this. Expectation operator, expectation of A plus B, what that would be equals to expectation of A plus expectation of B. So you can take the average like this. So instead of finding the diode current, I would be commenting on average value of resistor current and the average value of capacitor current. Understandable? Now what is the time constant here? What is the time constant of this particular circuit? What is the value of RC? Just let me know what is the value of RC. RC value is 400 milliseconds. And what is this time period? Time period is, frequency is 50 Hz. So what will be the time period? 1 by 50, that means 20 millisecond. Okay. Now can you make this sinusoid waveform? Yes sir. This is how the sinusoid waveform will look like. Time period is 20 millisecond. So this will be 20, this will be 40, this will be 60. In that manner you can make this sinusoid, and peak value is 10 and minus 10. 10 and minus 10. Okay. Understandable? Now what will happen? First positive cycle would come up. Just as the positive cycle comes up, what will happen? Initially the capacitor is having 0 voltage. Initially capacitor is having 0 voltage. So here there is 0 voltage. Here there is some voltage which is greater than 0. So what will happen? Diode will turn on. Just as the diode has turned on, what will be the circuitry you will be getting? So just as the diode has turned on, this kind of circuitry I will be getting. Sir, here there is source and here there is resistor and here there is capacitor. So if I make the capacitor voltage waveform, the same voltage waveform would be there across the resistor as well. What I am saying is that I am making the capacitor voltage waveform. The same waveform would be there across the resistor as well. So just as the diode has come, then what will happen is that whatever the input voltage is there, the same voltage will be followed. Like if I have applied V in voltage, at the output the same V in voltage would come up if the diode is on. So if the diode is on, if diode is on, then V out would be equals to V in. I am calling this as V out, this as V in. So output will simply follow the input. So output will simply follow the input like this. It will follow the input like this. I am making this output waveform. This color is talking about V0 waveform. So I am making this V0 T waveform now. Okay. Now what will happen? At this point your capacitor has charged to 10 volt. Your capacitor has charged to 10 volt. Okay. And what is this time? This time is 5 seconds. So at 5 plus second, just after 5 seconds, what will happen? Sir, this is 10 volt, but this would become 9.99 volt. Since this has become 9.99 volt and this is your 10 volt, what will happen now? The diode would turn off. So diode has turned off. Now if the diode has turned off, then what will happen? If the diode has turned off, then this is how the RC circuit would look like. This is how the RC circuit would look like. This is your C, this is your R. This has been charged to 10 volt. Now what will happen is that this will try to discharge. This 10 volt will try to discharge through the resistor, right? So it will be discharging. It will be discharging in this manner. 10 volt was the initial voltage, e to the power minus T by tau. What is the value of tau? Tau value is 400 millisecond. But now you see that, sir, let's just say it has started discharging, but it will discharge very slowly compared to the input. Are you able to understand this point? Are you able to understand this point? Input is changing very fastly with the frequency 50 Hz. That means in 20 milliseconds it will change a lot of values. But sir, our output, let's just say we have started from here. This is your 5 second, and let's just talk about 20 millisecond. Let's just talk about 20 milliseconds. So at 20 millisecond, what will be your capacitor voltage? Sir, it would be e to the power minus 20 by 400, right? So calculate the value of e to the power minus 20 by 400. Just calculate the value in your calculator. So you will see that it is nearly coming around plus minus into 10. It is coming around 5.1. So at 20 millisecond, this value has reduced to 5.1 only. Sorry, not 5.1, 9.51. Sorry, what I have put here. Yeah, 9.51. Sorry guys, 9.51. So this value has reduced to 9.51. Now it will reduce more, it will reduce more, it will reduce more. It will keep on reducing. Let's just say till this point. After that, what will happen? Let's just say it has reduced to 9.3 volt. Now 9.3 volt. Now this is your 9.3 volt, and let's just say this time is some 23 second. So after 23 second, what will happen? At 23 plus 1 second, what will happen? Input voltage would become 9.31 volt, and capacitor is having 9.3 volt. Then what will happen? Diode will again turn on. If diode is again turning on, then what will happen? Again it will charge. So again it will follow the input. Then again capacitor will reach 10 volt. At the input 9.99 volt would be there. Again diode would turn off. Again diode would turn off. Again discharging would be there. Again the same scenario would take place. So this kind of waveform we will keep on getting. This kind of waveform we will keep on getting. Now you will just look at this much of graph. Just look at this much of graph. Isn't it periodic? So this is the voltage waveform you are getting. This is the voltage waveform you are getting across the capacitor. Across the capacitor you can say, or across the resistor also you can say. So this is the waveform you are getting across the capacitor and across the resistor. Now what will be the current in the capacitor? This is the waveform. This is your, let us just say, VC waveform or V0T waveform at the steady state. This is not the steady state. This is the steady state, right? This is just the initial first cycle. First cycle is never the steady state. Steady state, at the steady state you see that this kind of graph you are getting. Which kind of graph? So at the steady state, this kind of graph I am getting. This kind of graph I am getting. This is my steady state graph, which is periodic. So this is my 10 volt. This is nearly equals to 10 volt, right? Nearly equals to 10 volt. Nearly 10 volt only we will have to take. So this kind of graph I am getting, sir. This is my VCT graph. Now I need to find out the average value of current. I need to find out. So what I need to find out? First I will find out the ICT value. What that would be? Sir, C dVCT by dt. So first I will find out the current. Now I need to take its average. Now I need to take its average. Similarly, I will find out IRT as well. What that would be? Sir, VCT divided by R. And once I will find out this particular thing, then I will take its average. Okay. Now this is my task. Now just let me explain you one very interesting thing, that there is a function called xt, which is periodic. If it is periodic, then you would know there is a concept of a Fourier series. If it is periodic, then you can write it down somewhat like this, that it can be broken into some DC value plus some sinusoid or cosinusoid. Here some sinusoid or cosinusoid would come. Sinusoid plus cosinusoid. Right? Xt is periodic. It can be written in some DC value and sinusoid plus cosinusoid. Now if you differentiate it, what will happen? dxt by dt if you do, what will happen? What is the differentiation of DC? 0. So this will be gone. Sinusoid, what you will be left with? Differentiation of sinusoid is cosinusoid. Basically here sinusoid and cosinusoid would come up. Only this much part would come up. This would be gone. This would be gone to 0. So if I ask you what is the average value of dxt by dt? What is the average value? Average value means DC value. What is that? That is 0. So from here, what is the conclusion you are making? That sir, if xt is periodic, then dxt, then average value of its differentiation, average value of its differentiation would be equals to 0. Is that clear to you? Say yes or no. If xt is periodic, then average value of its differentiation would be 0. VCT is periodic. dVCT by dt would be 0? No. If VCT is periodic, then this differentiation will not be 0. But if I take its average, my scenario is that my ICT is C dVCT by dt. If I want to take the average, what will happen? Average of ICT. If I need to take the average of ICT, if I need to take, what I will get? C into average of dVCT by dt. This is something I will get, right? Now what will be the average of this particular thing? Sir, I know that VCT is periodic. You take any periodic waveform in your life, whatever the periodic waveform you have seen, you take any periodic waveform and you differentiate it. What you will get? Always you will get average value to be 0. So what does that mean? That average value of capacitor current is equals to 0. Now I will say two statements and you need to tell whether the statement is true or not. Okay, one statement. At the steady state, first statement is at the steady state the capacitor current is 0. At steady state capacitor current is 0. Is that statement correct? No. Second statement, at the steady state the average current through the capacitor is 0. At the steady state the average current through the capacitor is 0. Yes sir, I see average is 0 but not the capacitor current is 0. Like at every place what I have seen is that they have said that at steady state the capacitor current would be 0. So whatever the current across the resistor you are getting, that would be the drain current, that would be the diode current, and your job is done. Absolutely baseless explanation. At the steady state you need to find out the average value. So at the steady state capacitor voltage is periodic, that's why its average current is 0. Current is not 0. What will be the current? Current will be simply the differentiation of this multiplied with C. So how you can say it is 0? But if you take its average, that would come out to be 0. So what did you understand here is that this value has came out to be 0. A lot of time in the interviews as well, if some good analog company is there, they will take the interview. If I am the interviewer, I would surely ask this particular question, that there is a periodic waveform at the input, this is my capacitor waveform, let me know what will be the value of current at the steady state. If he says 0, he is rejected. Sir, the value of current at the steady state, sir, I can draw the diagram, but it is not 0. But sir, if you take the average of it, it will come out to be 0. Okay, so the average value came out to be 0. So now what is the scenario is that our diode current, our average diode current would be equal to the resistor current only. Now what is my resistor current? So resistor current is the value of the capacitor voltage divided by the resistance. Now you know that sir, value of capacitor voltage is periodic, like from 10 volt to it is going down to some other value as well, but it is nearly equal to 10 volt only, no? So kind of you can say that sir, the value is nearly constant to 10 volt, nearly it is constant to 10 volt. So at the steady state you are getting nearly constant value. So nearly constant value you are getting, that value is 10 divided by the resistance value, that value was 100. So sir, average current at the steady state, average resistance current at the steady state I am getting as 0.1 ampere. So sir, this current is nearly around 0.1 ampere, nearly approximately is 0.1 ampere. So this current would also be approximately 0.1 ampere. So the answer was 0.1 ampere. So this is a different explanation that I have given here apart from my class notes. Okay, in the class notes and on YouTube I have given this particular explanation which you can watch. Okay, here the complete like detailed explanation in 1 hour I have given. I have broken down it into, like, here I am drawing the current waveform as well. Like this current waveform also I have drawn. Are you able to understand this point? Like here I did not draw this current waveform, no, right? Here I am just simply telling that if this is periodic, this would be 0. But here I have drawn this waveform and then I have taken the average. So full time domain explanation I have given, and one more problem also I have framed here, which is related to this one, but this time the input is square wave. Here it was sinusoid, no, input was sinusoid, but now here I have made the input to be square wave. So this is also a good discussion which you can watch, but as of now here you would have got a different approach and you would have understood that yes sir, whatever that we were learning, now we have understood something new. Okay, so this question we have solved. Let's see what next we have. Yeah, this is the next question we have. We need to find out the small signal voltage gain. So I need some energy, I will take some break. You can also take some break. So after that break, I will solve this particular question and then we can see this particular question as well. Okay, and more questions are also there. So I will take some break and then I will come back. You also can take some break. Yeah, so now we will solve this problem, but before that you will answer me a few things and I will teach you a few things. Okay, so first let me know what kind of circuit it is. It is a PMOS or NMOS? It is a PMOS or NMOS? Sir, arrow is outside, it is NMOS. What about this one? Sir, this will be PMOS. Okay, now let's just say I say this potential is V1 and this potential is V2. This potential is V1 and this potential is V2. Now in the MOS circuitry, this current I need to write down in the downward direction. So what will be value of this current? So it would be Gm into this potential V1 minus this potential V2. The current is going from upward to downward. Kind of you can say that from V1 to V2, from upward to downward, Now if I write down this particular current, and you know one more thing, that whatever the current that is flowing here, the same current would be flowing here as well. So this current would also be Gm into V1 minus V2. In the MOS, the current would be same, and in MOS this current would be 0 ampere. This all these things you already know. This current would be 0 ampere. Now if I ask you what will be this current? Current going in the upward direction. The circuit is same. Can you let me know that this current? Sir, it would be negative of this. downward direction current is GM V1 minus V2. So upward direction current would be GM V2 minus V1. Sir, it is pretty obvious why you are asking it. But if I need to write it down, so how would I write down? I am going upward. That means I am going from V2 to V1. So what I will write down? GM V2 minus V1. Like it's just a way. There you don't need to think that sir V1 minus V2, V2 minus V1. You see the current direction. Current is going upward. GM V2 minus V1. Similarly here, let's just say this potential is V1 and this potential is V2. Not this potential, sorry, this potential. Because gate and source potential we need to define. So this potential is V2, this potential is V1. Now I'm asking you what is the current in the downward direction. Whatever the current is there, the same current would be here as well. So what is the current in the downward direction? What you would say? So I'm going from V2 to V1. So current would be GM V2 minus V1. Now again the same circuitry is there, did to same, nothing changed. But just I'm asking you what is the current in the upward direction. Whatever the current that is flowing here, the same current would be flowing here as well. Similarly, whatever the current that was flowing here, the same current would be flowing here as well. So what is the current? You would say that sir, current would be GM. I'm going from V1 to V2. V1 minus V2. That's it. So VGS, VSG, all these things you don't need to see. Just see the current direction from where to where you are going. That's it. V1 to V2, GM, V2 to V1, GM V2 minus V1. V1 to V2, GM V1 minus V2. Same current would be flowing here as well. Well and good. Now another very small thing. There is a potential V. From this potential V, I current is flowing. So what will be the value of this resistance R? From potential V, I current is flowing. So the value of this resistance R is V by I. Similarly, if I say from this potential V, GMV current is flowing. So what will be the value of this resistance R? The resistance R would be from the potential V, GMV current is flowing. The resistance R would be 1 by GM. Well and good. So I will be using it somewhere. Let's get started with the question now. Small signal gain we need to find out. We always have to move from V1 to V0. Sorry, not V1 to V0, V into V0. What we need to find out? We need to find out V0 and V in. So our matter of concern is V0 and V in. So my target would be that sir, I move from V in to V0. That's it. Whatever that is coming in between, that I need to eradicate. So let's get started. What I would do? First, I need to do the AC analysis. So what I would do is that this VDD would be grounded, right? And then this circuit is there. If I make in this manner, then it would take a lot of time. So I need to make it quick. This is my V in. Okay. And downward, if I look, okay, now this is your V0. Now this is your V0. Now where will be your R0? Sir, R0 will be somewhere here. R0 will be between drain and source. So drain is connected to, sorry, source is connected to V0 and drain is connected to ground. So this will be my R0. This is M1, so R0 1. This is your M1, this is your M2. And V0 to ground, this would be your R0 2. Well and good. Right. Now what do you see? From V0 to ground, I see R0 2. From V0 to ground, I see R0 1. Now this potential is V0, right? This potential is V0. Now if this potential is V0, can you write down this current? This potential is V0, this potential is 0. What will be this current? So this current would be, I am calling this current as I1. Okay. So this I1 current would be, sir, GM into, I am going from V0 to ground, GM into V0 minus 0. So this, sir, this I1 current would be nothing but GM V0. So this is your V0 potential. In from this V0 potential, how much current is flowing? GM V0 current is flowing. From this V0 potential downward, there is GM V0 current is flowing. So from V0 to ground, what you can assume? You can assume a resistance. What will be value of this resistance? So that would be from V0 resistance. So sorry, from V0 potential, GM V0 current is flowing. So that value will be 1 by GM. There you go. So what you see? From V0 to ground, sir, I see R0 2. From V0 to ground, sir, I see R0 1. From V0 to ground, sir, I see 1 by GM1. This is GM1, no? GM1, GM1, GM1. So from V0 to ground, what all things you see? R0 2, R0 1, 1 by GM1, and then this circuitry. What will happen to this circuitry? We will see that. But how you can reduce this circuit now? Sir, the reduction I have done in this manner. In what manner? This circuit remains as it is. This is my V in. I will have to add a page because it would not look good. Okay. What I do is that yeah. So I will have to add some page. So how I have reduced the circuitry? I have reduced the circuitry in this manner, sir. This M2 remains as it is. I cannot do anything about M2 as of now because M2 is connected with V in. Now here it is connected to V naught. This was grounded already, right? This is the scenario. This is your M2, V in, grounded, all these things fine for you. Now from V naught, what I have seen, from V naught to ground I see R naught 1, from V naught to ground I see R naught 2, from V naught to ground I see 1 by GM1 as well. That means from V naught to ground, what all things I see? From V naught to ground I see R naught 1. From V naught to ground only, from V naught to ground I see R naught 1, from V naught to ground I see R naught 2, from V naught to ground I see 1 by GM1 as well. That means all are coming in parallel. So you can effectively you can say that from V naught to ground I see R naught 1 parallel with R naught 2 parallel with 1 by GM1. Say yes or no. This is what we see. Well and good. All fine. Now this is your V. This is your 0. Can you write down the current? If I want you to write down this current coming from upward to downward, what that current would be? So that current would be GM2, upward potential is 0 minus V in. So this current, whatever the current that is flowing here, the same current would be flowing here as well. So this current has become, what this current has become? This current has become minus GM2 V. This current has become minus GM2 V. Now the same current is flowing through this resistance as well. How much current is flowing through this resistance? Minus GM2 V. So what is the value of V naught now? The current is flowing in this direction. That means this will be the value of V naught. Value of V naught would be current, which is GM2 V in, multiplied with the resistance R naught 1 parallel with R naught 2 parallel with 1 by GM1. So what is the value of V naught by V in you are getting? Sir, I am getting this as minus GM2 parallel with R naught 1 parallel with R naught 2 parallel with 1 by GM1. So minus GM2 1 by GM1. This is the answer. Always look at V naught, look at V in. Whatever that you can reduce, just reduce that and then simply apply the equations, you will get the answer. Detailed discussion, we will solve another problem here. But after that, like before that only I am telling, there is a detailed discussion done on MOSFET amplifier. Like even if you have zero knowledge of MOSFET amplifier, still you will be able to understand. So this is a must watch video for everyone. This I uploaded last year, so you can go solve MOSFET amplifier within a minute. So even if you have zero idea of analog electronics, still you will be able to understand this particular video, and it will be coming for either 2 marks or 4 marks in the examination. So must watch video it is. You can see views are also pretty good. 15K views are there. So you would be able to understand in a much better manner. Even if you have studied MOS amplifier, then also it will be revised in a much better manner without drawing any model. Like this is how we need to consider all the cases. So all the cases I have considered there, and all the gate PYQs also you will be able to solve after this particular video. So surely you need to watch this particular video. Let's solve this particular question now. So what is happening in this one? Again, sir, my eyes will be on V naught and V in. Sir, in between, sir, from V in to I see RS, then sir, at this node there is some issue. Sir, at this node there is RB connected and then this circuitry is connected, sir. But I can see my V naught and V in, this is the relation. So somewhere there is a issue. Let's call this node as a VA node. Okay. Now from VA node I see RB, but sir here I see some circuitry. Okay. Let's call this node as VB node. So from VB node, what do we see? I am making that particular circuitry. From VB node, what do I see? From VB node, sir, you see a current source. And then you see this particular MOS circuitry. Which circuitry? This particular MOS circuitry, sir, you see. This is my VP. Okay. And this was your VDD. Now you know one thing that, sir, if I am doing the AC analysis, then this will be open circuited, this will be gone, and this will also be gone. So effectively, this kind of circuitry I see. Effectively, this kind of circuitry I see from VB. Now you know that from VB, whatever that you see, that has to be replaced with some resistance, right? Then what will happen? RB in series with some resistance, and VA node will be simplified. So if this node is VB, this node will also be VB. Now if this node is VB, then how much current it will drive here? This MOSFET is M1. So how much current we will get here? Sir, that would be GM1 VB. Understandable? If this current is GM1 VB, Then how much will be this current? That would also be GM1 VB. How much will be this current? That would also be GM1 VB. So this current is GM1 VB. Right? Is that understandable to you? Now just let me know how much will be this current. Sir, 0 ampere. So this current is 0 ampere, this current is GM1 VB. So how much will be this current? Sir, this particular current would be nothing but GM1 VB only. So what do you see here? From the VB potential, I am driving GM1 VB current. So if I need to replace it with some resistance, what will be the value of this resistance? The value of this resistance would be, sir, I am from the VB potential, I am driving GM1 VB current. So the resistance will be 1 by GM1. So this much of whole circuitry, can simply be replaced with 1 by GM1. Is that understandable to you? Is that understandable to you or not? Yes, sir, surely it is understandable. Now from VB to ground, you see 1 by GM1. So from VA to VB, you see RB, and RB is coming in series with 1 by GM1. From VB to ground, 1 by GM1 you see, no? So RB and 1 by GM1 will be in series. So from from VA to ground, what do you see? From VA to ground, what do you see? So let's make the circuitry now. What we are having? Here we are having V in, right? We are having V in. Now after V in, there is RS connected. From V in, there is RS connected. Then sir, there is VA. So from VA to simply RB is connected, right? From VA to simply RB is connected. This was your VA node, right? Then this was your VB node. From VB to ground, what is there? 1 by GM1 is there. 1 by GM1 is there. This is the scenario. Now after that, what is the scenario? After that, there is simply M2 connected, and then from M2, that VDD will also be ground. This will also be grounded. So sir, this node will become V node, and this will be my RD. Okay, this is the scenario now, right? V node to ground, you see RD. From V node to ground, you see RD. So this is how I can make it. Now can you write down this? Let's remove this VB now, because now I see that this is the total resistance RB plus 1 by GM1 I see. Can you write down this VA potential in terms of V in? Yes, sir. What will be this VA potential? Sir, VA potential will be RB plus 1 by GM1 divided by RS plus RB plus 1 by GM1 into V in. Say yes or no. Can you write down this particular equation? This is your VA. RB plus 1 by GM1 upon RB plus 1 by GM1 plus RS, that is multiply with V in, would be equals to VA. Now if you know VA, can you write down V naught? Now this much of basics would be clear to you. Sir, if this is VA, then what will be this current? If this is your VA, and here R naught is ignored, okay, channel length modulation is ignored, so R naught we are not considering. If this is VA, so then sir, this current would be GMVA, because this potential is VA, this potential is 0, that means this current would be GMVA. Now the same GMVA current would be flowing here as well, it would be flowing here as well. So this would be GMVA current is flowing. What kind of MOS it is? It is M2, so it would be GM2VA. So what will be the value of V naught? Value of V naught would be, current is flowing downward to upward, so the drop would be somewhat like this, right? So the voltage would be minus GM2VA, that is the current, multiply with the resistance, that is RD. So what you are getting? V naught is minus GM2RD into VA, that is your V naught. Okay, that is your V naught. Now VA I can replace in terms of V in. So minus GM2RD RB plus 1 by GM1. Now in what form answer is given? Yeah, in this form only answer is given. So you can sense that sir, answer is matching now. I am just replacing the value of, I am putting this value of VA here, nothing else. So RB plus 1 by GM1 upon RS plus RB plus 1 by GM1, multiply with V in here, and this is equals to V naught. So V naught by V in, what is your V naught by V in coming out to be? So your V naught by V in is coming out to be minus GM2RD minus GM2RD. They are talking about the magnitude, okay? They have just taken the magnitude here. They have taken the magnitude. So what you will get? GM2RD, RB plus 1 by GM1, RB plus 1 by GM1 plus RS. RB plus 1 by GM1 plus RS. So this option is matching. Okay, if you have more than enough practice, no, then these will not take much time. you would see, sir, RB, the 1 by GM1 is there, so RB plus 1 by GM1, simply the drop would be there and then multiply with GMRD, that's it. Very easily you will be able to do it. Like these are very standard circuits, no, all these things are very standard circuit. So you have reached to this level, then it will be simply a cakewalk. So in the examination, it will not take much time. So this question is also clear, okay? And surely you need to watch this particular video. Here you will get a clear idea, all the PYQs are also solved in 3 hours. After that, you will feel like that, sir, if the question is coming on MOS amplifier, I will be able to solve it. Okay, even if you have zero idea of analog, zero knowledge of analog is there, no, then also you will be able to understand. Okay, let's go to the next one. Great question, absolutely brilliant question. You might have solved it applying some formula. I don't know which formula you would have applied. 2RC ln 1 plus beta 1 minus beta, whatever the formula it is, you would have solved it with respect to the formula. But in the analog, I never believe in formula. So I'm not going to solve it with respect to the formula, but I am going to teach you a very good concept. Now, CMOS Smith trigger is given and it is inverter. So there are two kinds of Smith trigger, inverting Smith trigger and non-inverting Smith trigger. So let's discuss that. What do you mean by inverting Smith trigger? What do you mean by non-inverting Smith trigger? So we are going to discuss non-inverting Smith trigger. Symbol is like this. This is the symbol of a non-inverting Smith trigger. Now it has two kind of voltage, upper threshold voltage and lower threshold voltage. You need to have a basic idea of a Smith trigger, then you will be able to understand. So it has two kind of voltage, upper threshold voltage and lower threshold voltage. Let's just say this is my lower threshold voltage. Let's call it -2 and let's call it +3. So this is your lower threshold voltage, which is -2, and this is your upper threshold voltage, which is +3. Now what is the meaning of a non-inverting Smith trigger? Non-inverting Smith trigger means if your value is, if your input is, this is your input Vin and this is your output V0. If your input is greater than 3 volt, then your output will be high. Let's just say high potential is 5 volt and low potential is -5 volt. Okay. So if your Vin is greater than 3 volt, then output will be +5. And if your Vin is less than -2 volt, then your output would be -5. That means for higher values of input, you will get the higher output. If your input is greater than 3 volt, then this is the output you will be getting. And if your input is less than -2 volt, then sir, this is the output you will be getting. This is the output you will be getting, which is -5. Now sir, what will happen in between? That's the question. In between, what will happen? So in between you get the dead zone. This is known as dead zone. So in between you get a square. Now what is the meaning of this square? I will explain it. Have some patience. This kind of characteristics you will get in between. This kind of characteristics you will be getting in between. So this is your +5 volt you are getting here and -5 volt you are getting here. Okay, so if your input is greater than 3 volt, then +5 volt, input is less than -2 volt, then -5 volt. Now sir, what do you mean by this particular characteristics? I will tell you, but before that, let me tell you one more thing, that if it is non-inverting Smith trigger, then the rotation will be anti-clockwise. What do you mean by this rotation, sir? That also I will tell you. The hysteresis, this is known as hysteresis, that will be anti-clockwise. For non-inverting, it will be anti-clockwise. And here, both clockwise and anti-clockwise, both nature would be there. Now, let's just break down this particular characteristics. What I am doing, I am breaking down this particular characteristics. Just follow this particular sign, forward sign. If you follow this forward sign, then this characteristics you are getting. Say yes or no. Only follow the forward sign, don't follow the backward sign. If you only follow the forward sign, then this is the characteristic you are getting. So this is one characteristic that I have broken down in this manner. That if I only follow the forward sign, this voltage is 3 volt. If I only follow the forward sign, then this is the characteristic I am getting. If I only follow the backward sign, then this is the characteristic I will get. Only follow the backward sign, this is the characteristic I will get. So this point is -2 volt. Understandable? Well and good. This is 3 volt -2 volt. Higher value will give you output of +5 and lower value will give you output of -5. When you combine both of them, you get this particular characteristics. Okay. Now, how to read this particular characteristics? What is the meaning of this characteristics? If I ask you, my Vin is 4 volt, what is your V out? Sir, if your Vin is 4 volt, this characteristics is saying that your output should be +5 volt, and this characteristic is also saying that your output should be +5 volt. if your Vin is minus 3 volt, what will be my output? Sir, if your Vin is minus 3 volt, then this characteristic is saying that your output should be minus 5 volt, and if your Vin is minus 3 volt, then this characteristic is also saying that your output should be minus 5 volt. In both of the cases, you are sure about the output. But let's just say someone says that my Vin is 0 volt, what will be the output? Sir, when your Vin is 0 volt, then this characteristic is saying that your output should be plus 5 volt, and this is saying that your output should be minus 5 volt. So who is correct? Sir, this particular characteristic that you have made, that will follow both of the cases, no? So which one is correct? You need to ask from where you are getting this 0 volt. Now if someone says that you have moved from plus infinity, or take any value, from plus 10 volt to 0 volt, you have changed your input from plus 10 volt to 0 volt, plus 10 to 0. Initially you were here, let's just say this is plus 10 volt. Initially you were here, and you have moved from plus 10 to 0. That means in which direction you have worked? In this direction. So this is the arrow. So now you need to follow this particular characteristics. Here if you have moved, let's just say this is 10 volt. So 10 to 0. So how you are moving? You are moving in this direction. But here the arrow is saying that you need to move in this direction. Are you able to understand this point? You are moving in this direction, but arrow is saying you need to follow the opposite direction. That means this characteristics I will not follow. I will follow this particular characteristics. Okay, so if Vin is moved from plus 10 to 0 volt, then when Vin is equals to 0 volt, then what will be your output? Then my output would be, sir, I will follow this particular characteristics, and he is saying that output will be plus 5 volt. Now if your Vin is moving from minus 10 volt to 0, then which characteristic you will follow? From minus 10 to 0. That means arrow will be in this direction. And now if your Vin is 0 volt, so what will be your V naught? V naught will be minus 5 volt. So what do you understand from this characteristics? That if I am moving from a low value to higher value, then I will not change my output until I reach to the upper threshold voltage. And when I am moving from higher voltage to lower voltage, I will not change my output until I reach to the lower threshold voltage. You don't need to mug it up. What you can do is that you can always make these characteristics. You will say that, sir, it is non-inverting symmetric trigger. At higher value, I will get higher output. Lower value, I will get lower output. In between, I will get a square. Okay, not square, it could be anything. This particular characteristic I will be getting in between, right? Since it is non-inverting, I will have an anti-clockwise characteristics. Now, I will be able to read this particular characteristics. What this characteristic is saying, that for any value greater than 3 volt, output is 5. For any value less than minus 2 volt, output is minus 5. In between, you need to tell from where to where I am moving. If I am moving from higher voltage to lower voltage, higher to lower, then I will follow this particular characteristics. If I am moving from lower to higher, then I will follow this particular characteristics. There you go. This is the meaning of non-inverting symmetric trigger. But in the examination, inverting symmetric trigger was mentioned. So let's understand about inverting symmetric trigger now. Yeah, an inverting symmetric trigger. Okay. So what is the meaning of inverting symmetric trigger? So again, I am saying that my upper threshold voltage is 3 volt and lower threshold voltage is minus 2 volt. What is the name here? Inverting. So what will happen? If my input is high, my output will be low. Let's just say with respect to high output, I am getting plus 5 volt, and with respect to low output, I am getting minus 5 volt. So if your input is greater than 3 volt, then output will be low. That means it will be minus 5. And if your input is less than minus 2 volt, that means if it is lesser, then your output will be higher, which will be plus 5. Is that understandable to you? Minus 2 plus 5, greater than 3, you will get minus 5. In between, what you will get? In between, you will get a square. In between, you will get a square like this. In inverting symmetric trigger, the rotation will be clockwise. Rotation will be clockwise. Okay, here both of the arrows would be there, here both of the arrows would be there. Sir, how do we get this particular characteristic? If you want to know this particular thing, that sir, how I am getting this characteristics, then you need to watch this video. Okay, even if you have zero idea about symmetric trigger, then also you will be able to understand. Like a lot of people would study symmetric trigger, but they don't study it in a good manner. No matter from whichever the god educator you are studying, a lot of legendary educators are there in this field. But if you study from human being, you will realize that there is a different meaning of symmetric trigger. A way different meaning of symmetric trigger is there. Please watch this particular video. You will understand the meaning of symmetric trigger. That how we started. Actually, we started from this particular characteristics. that we needed to make these characteristics, then we join them and then we move to Schmidt trigger. Okay, that is the actual flow of studying Schmidt trigger. But we will put a particular circuitry, we will analyze it that this much higher output doesn't make any sense. So please watch that particular video. Okay, please watch that particular video. You will have a much clear idea about Schmidt trigger. Okay, so yeah, this particular thing we have seen. Yeah, so how would you read this particular characteristics? You would say that, sir, if my input voltage is greater than 3 volt, output will be surely minus 5. If it is less than minus 2 volt, output will be surely plus 5. Now, if my input is moving from a higher potential to lower potential, then my output will be changing at a lower threshold value. And if my output is changing from, if my input is changing from higher potential to, lower potential to higher potential, if my input is changing from lower potential to higher potential, then the transition would take place at a upper threshold voltage. So if I am following this particular thing, that means I need to follow this characteristics. And if my input is following this particular thing, then I need to follow this particular characteristics. Is that understandable to you? Let's solve the question now. In the question, what they are saying, read the question. They are saying that inverter is having low output level of 0 volt and high output level of plus 5 volt. Low output level of 0 volt and high output level of plus 5 volt. 0 volt here and high output level of plus 5 volt. Is that understandable to you? This is what they are saying. So two possible outputs are there, either plus 5 you can get or you can get 0 volt. Two possible outputs are there. Right? What is the upper threshold and lower threshold voltage? These are 2.4 and 1.6. It is not necessary that it has to be negative. It can be positive as well. But upper threshold voltage is 2.4 volt and lower threshold voltage is 1.6 volt. Sir, what kind of Schmidt trigger it is? Inverting Schmidt trigger. CMOS inverter it is, no? So it is your inverting Schmidt trigger. Inverting Schmidt trigger. Can you make the characteristics now? Surely I can make the characteristics. Sir, this is how I will be making my characteristics. I can get, sir, two kind of output, either plus 5 or 0 volt. Either plus 5 or 0 volt. Sir, I am having lower threshold voltage of 1.6 volt and upper threshold voltage of 2.4 volt. Sir, if I make the characteristics, it would look somewhat like this. Sir, in between both of them, sir, I will be getting a square. Between upper threshold and lower threshold, you always get a square. Upper threshold and lower threshold. Upper threshold and lower threshold, you always get a square. Between upper threshold and lower threshold, you always get a square. Now, if input is greater than 2.4 volt, if input is greater than 2.4 volt, let me know what will happen. It is inverting Schmidt trigger. So for greater value, you will get lower output. For greater value, you will get lower output. And for lower value, you will get higher output. Okay. And sir, this is output will be plus 5 volt and this output will be, sir, 0 volt. Sir, this is what? This is inverting Schmidt trigger. That means rotation will be anti-clockwise. Sorry, clockwise. Sorry guys. It is clockwise. For inverting Schmidt trigger, rotation will be clockwise. Okay, and here both clockwise, anti-clockwise, both full follow. But here there is no meaning of rotation. You don't need to make the rotation. You know that if input is less than if input is less than 1.6 volt, job done. If it is greater than 2.4 volt, then also you know. In between, what is the scenario that you need to know. So here also both kind of rotation you can make. Okay. Now what they have done, they have taken this particular circuitry only. What they have done is that they have simply taken this particular circuitry only. And they have connected a feedback. What kind of feedback they have done? They have connected a RC circuit here. Okay, and then this node goes here. This is the circuitry. Say yes or no. 10 kilo ohms, 47 nanofarad. Right? This is the scenario now. Now let's see what will happen. What is the initial voltage across the capacitor? That is 0 volt. So this voltage initially at t equals to 0. What we are doing now is that what we will do now, We will draw the V in waveform as well, and we will draw the V out waveform as well. Both of the waveforms we will draw, but I will have to add a page which I am not having as of now. So what I can do is that I can take up this page. पेज तो है ही नहीं यार, कहाँ ड्रॉ की जाए? Where do I place it? So what I am doing is that I am removing this particular page. Okay, removing this. Like you can see, two videos are there. Both of the video you should watch. After watching this particular video, you can watch this video and this video as well. Okay, so these two videos you can watch. So I am removing this slide, and MOSFET amplifier also you can watch. So I am removing this slide as well. So I will get 2 extra pages. Yeah. So now what I am going to do is that I am going to draw V in versus V naught waveform. Like V in waveform also I will draw, and V naught waveform I will draw with respect to time. V in waveform also I will draw, V naught waveform also I will draw with respect to time, and V naught T with respect to time. Well and good. Okay. So initially at t equals to 0, what is the input? 0 volt. Now if input is 0 volt, then what will be the output? So if your input is 0 volt, output will be plus 5 volt. So initially at t equals to 0, your output is plus 5 volt. So at t equals to 0, your output is plus 5 volt. After that, what will happen? I don't know, but I will be starting from here, and my input is 0. Right? Now just as it has become 5 volt here. Now this is the ideal op-amp. Everything is ideal, so this current would be 0 only. This current, all this current would be 0. Now what is the scenario here? This is 5 volt. Now what this 5 volt will do? This 5 volt will charge this capacitor now. The scenario is you are having 5 volt here. This is resistance R and this is C. So now this 5 volt will charge this capacitor C. How it will be charging? Let's call this is your input, V in input only. So your V in T would be nothing but 5 into this equation. You need to know how you can write down this particular equation. I think this much is clear to you. How to write down the charging capacitor equation. 5 into 1 minus e to the power minus t by tau volt. What is the value of tau here? RC value is 470 microsecond. Okay. So your V in T is nothing but 5 into 1 minus e to the power minus t by 470 micro. Okay. Now this capacitor will start developing some voltage. That means what is happening now? The input value, this input value is increasing from 0 to some particular value. So what is happening? Your input value is increasing from 0 to some particular value. That means which characteristics you will follow? This characteristics I will follow. So it is increasing from 0 to some particular value. Is that understandable to you? Now what will happen is that when input is 0 volt, output will be plus 5 volt. When input is 1 volt, output will be plus 5 volt. When input is 1.8 volt, output will be plus 5 volt. When input is 2.1 volt, output will be plus 5 volt. But when the input become 2.41 volt, what will be the output? Not minus, output will become 0 volt. Is that understandable to you? Sir, initially this was 0 volt, output was plus 5 volt. Now this plus 5 volt has started charging this capacitor. Now the capacitor is getting charged. If the capacitor has reached to 2.4 volt, from 0 to if it has reached to 2.4 volt, then the output will change. This output will change. If this output is changing, then something different would happen with RC circuit. So what you have understood, until your V in T is reaching 2.4 volt, no changes are happening. This will remain 5 volt only. That means this will remain the charging condition only, and you can get the value of T from here. So what will be the value of T you will be getting, that you can see. (2.5 divided by 5 minus 1 plus minus 2.5 divided by y minus 1 plus minus ln into 470 micro. So 307.34 microsecond it would take, although it is not a matter of concern for me, but still if I need to make the waveform, 307.34 microseconds. Again let me check the calculation. 2.4 divided by 5, and then minus 1 goes here, then you take ln and then you multiply with 470. Yeah, so 307.34. So for 307.34 seconds, it will remain at plus 5, then it will become 0. Now till what point it will remain at 0, that we will see, but till how much time, how much was this window? This window was 307.34 seconds. 34 surely microsecond. All these calculations are going into microsecond. And what about the input voltage? Sir, input voltage started with 0 and it has charged to 2.4 volt. It has charged to 2.4 volt. It has charged to 2.4 volt. Till what point? Sir, till the same time that is 307.34 seconds. And after that, what will happen, that we will see. So this is your 307.34 seconds. Now after that, what will happen? And this has charged to 2.4 volt. Okay. Now this has become 2.4 volt or just greater than 2.4 volt, or you can say that it has become 2.4000001 volt. Then what will happen? Output will become 0 now. Output will become 0 volt now. Now what is the scenario? The scenario is that, sir, this capacitor, which is 47 nanofarad capacitor, sir, this has been already charged to 2.4 volt. This is already having 2.4 volt, right, sir? And now then there is a resistance R. Then there is a resistance R. And sir, this node of resistance R is actually grounded now. This is the scenario. Now what will happen? This capacitor will discharge. Right? Now the capacitor will discharge. So how it will discharge? What will happen to this V in T? Output is at 0. What will happen to this V in T? So now the V in T equation would be, from 2.42 it will discharge. Although it will be starting from, sir, 307.34 seconds. So ideally you should write down the equation in this manner, that e to the power minus t minus 307.34 divided by tau. But I am ignoring this particular part. Like, I don't need to care about this particular part, no, 307.34 seconds. I would just get to know that I am considering this is my t equals to 0 now. Okay. So I am simply writing down that capacitor will discharge now. So capacitor will discharge. Capacitor will discharge in this manner. Okay. That means now this value of V in T is decreasing. 2.4 it is. So from 2.4 to somewhat lesser you are going. That means you are moving from 2.4 to some less value. So which characteristics you will follow now? Which characteristic you will follow? This characteristics I will follow now. From 2.4 to I am decreasing. So which characteristics? This characteristics I will follow now. Where the transition would take place. 2.4, let's just say it has become 2.3, output is still 0, output is still 0, output is still 0. If your capacitor voltage has become 1.6 volt, then what will happen? Output will change. This output from 0 to it will go to plus 5 volt. When this 2.4 has become 1.6 volt. So how much time it would take to go from 2.4 to 1.6? So that time I can find out. E to the power minus t by 470 microsecond. So how much time it would take? Sir, it would take 1.6 divided by 2.4 ln into 470. 190.56 microsecond. 190.56. So after this it will take 190.56 microsecond. How much? 190.56 microsecond. After this it will take 190.56. So in 190.56 you need to add up 307.34. Right? So that is becoming 497.90. Okay, so it has become 1.6 volt now. This has become 1.6 volt now, and the output is still at 0 volt only. But after that output will become plus 5 volt. So this is your 497.90. Now what will happen? Output has again become 5 volt. Output has again become 5 volt, and this capacitor is initially having 1.6 volt now. So now what is the condition? For the third cycle, the condition is that, sir, output has become plus 5 volt here. Then, sir, there is R, and then, sir, there is capacitor C as well. There is R, and then this capacitor C as well. But now this time the capacitor C is charged to how much voltage? It has charged to 1.6 volt, and this is my V naught. Now what will happen? This 5 volt will charge this capacitor. Say yes or no? Yes, sir. It will charge this capacitor. Now from 1.6 to where it will try to go? Sir, it will increase from 1.6 to this time the characteristics would go from 1.6 to it will try to increase. So from 1.6 to it is trying to increase in this manner. So where the transition would take place? At 1.7 output will be plus 5, 1.8 output will be plus 5, 1.9 output will be plus 5, 2.3 output will be plus 5. 2.4 output will change. That means when the input value become 2.4 volt, then it would change. So can you write down the capacitor charging equation? Can you write down the equation of V in T? What is your V in T? This is not V out, sorry. This is not V out. Here I have said V out it. This is not V out actually. This is V in T. The capacitor voltage is V in T here. So this is your V in T. So when your V in T would change, your V in T equation is, it will try to go to 5 volt. If you need to write down the V in T equation, this will be the V in T equation. Ideally, I know that, sir, it will be starting from some, this is 497.90 second. So ideally here in this equation, I should put T minus 490 whatever it is, but I don't care about that. I will simply find the time and then I will add it up. So I don't want to make my equation complex. So T by 2, which is 470 microsecond. Now where the transition would take place? At 2.4. e to the power minus T by 470 microsecond. So from here you can get the value of T. So 2.6 divided by 3.4 ln into 470, 126.08 microsecond. Okay, again 2.6 divided by 3.4 ln, 126.08 microsecond. That means what is happening, if I see this particular characteristics, it is going from 1.6 to again 2.4, and how much window it is taking? It is taking the window of 126.08 microsecond. 126.08 microsecond. So if I need to show this particular time, this time would be 497.90, 497.90. So 623.98, 623.98. Now this is the scenario we have got, and it has remained to, output has remained to 5 volt. After that, what will happen? Output will again fall down to 0. Why is that so? You can follow the characteristics. From 6 to 2.4 we have gone. From 6 to 2.4 we have gone. We were following this particular characteristics. So now the output will again fall down to 0. Now the output will again fall down to 0, and capacitor is already charged to 2.4 volt. This capacitor has charged to 2.4 volt now. Now what is the condition? The output has fallen down to 0. Output has fallen down to 0, and capacitor is charged to 2.4 volt now. Now have you analyzed this condition? RC circuit, capacitor is charged to 2.4 volt. RC circuit, capacitor is charged to 2.4 volt. Then what will happen? Again charging. Then again at 1.6 volt it will make the transition. What does that mean? That means this cycle now will keep on going. This cycle now will keep on going. Is that understandable to you? So after this, the cycle will keep on going. What does that mean? That means this particular window will keep on repeating. This is always, I say always one thing, that first cycle is never the steady state cycle. First cycle is that where the circuit is starting. After that you will get the steady state cycle. So this is the steady state cycle we will keep on getting. Decreasing, increasing, decreasing, increasing. So output will keep on making the transition from 2.4 to, what about output? Output will keep on making the transition from 5 volt to 0 volt, 0 volt to 5 volt, 5 volt to 0 volt with this much of time window. Now what is this time window? This time window is 190.56, 190.56 plus 126.08, 190.56 plus 126.08, that is coming out to be 316.64 microsecond. So this is the time period we are getting. What will be the frequency of oscillation? In the equation, what they are asking? Frequency of oscillations they are asking. Frequency of oscillation in hertz. So what you need to do? You need to take the reciprocal and then multiply with 10 to the power 6. 1, 2, 3, 4, 5, 6. So what I am getting? 3158.16 hertz. So that's the answer. That's the way of solving this particular question. Now someone would say that, sir, will we get this much of time? If you have enough practice, then you will be able to solve it in 3 to 4 minutes. What you would see if I have enough practice? Sir, non-inverting Smith trigger, make the characteristics. Now you know one thing, that sir, I will be starting from 0, output will be plus 5 volt. So first I need to know that these kind of questions would be there in your class notes as well. So you would know that, sir, first cycle will not be the steady state cycle. First this will charge to 2.4, then it will discharge to 1.6, 2.4, 1.6, 2.4, 1.6. This cycle will keep on going. So now my target would become that this is 2.4, so it will discharge first. It will discharge to 1.6. Then after reaching 1.6, here 5 volt would come and it will again charge. So 2 cycles only I will analyze, and I will be able to get this time value. Our matter of concern was, what was our matter of concern? This was our matter of concern. No, I will avoid this step. Where I would go, I would directly go to this particular step. That's why it will discharge this equation. I will write down, I will get the value of t. Then in this waveform, I would know that value of t is coming out to be 190.56 microsecond. Then sir, this particular equation will be my matter of concern. I will get this particular value 126.08. I will simply add them up and get the final answer. It depends on how much practice you are having. And now this was the concept of a vibrator, astable multi-vibrator. Okay, it was the concept of a multi-vibrator, astable multi-vibrator. Okay, so output is changing from 0 to 5 volt, 5 volt to 0 volt, 0 to 5 volt, 5 volt to 0 volt. So it is known as astable multi-vibrator. Okay, 5 to 0, 0 to 5. That means there is no steady state. Your output is continuously changing between 0 to 5 volt. So astable multi-vibrator we have studied. Okay, usually people apply the formula, but IIT's professor, when they are setting up the question paper, what they can do is that I have actually removed that particular slide. There one question I have framed. No, there was this kind of question was there in the slide where I showed you. Like I have removed that particular slide, but I told you to remember. I told you to watch two videos. One was based on op-amp, other one was based on some question. So that was also based on astable Smith trigger only, astable multi-vibrator only. So these kind of question, if they frame, then your formulas will not work there. So always remember one thing in analog. Remember zero formula. They can always frame some question where formulas will not work. Okay, so take care of this particular thing, that don't depend on the formulas, depend on the analysis. Okay, so we have solved this one, then we need to solve this one as well. It is a simple question, but detailed analysis will be interesting. So in this video I am not going to do the detailed analysis I have already made, but here I will tell you that how to approach this question in the examination hall. So I will do it, but I will take some break. So after taking some break, I will again come back. You can also take some break. Okay, then we will see this particular question. Yeah, so let's see the solution of this one. Here, what is the scenario? First thing is that, sir, 1 microfarad, sir, it will become 2 microfarads. Both are in parallel, it will become 2 microfarads. So this is how I can reduce my circuit. There is a V input there, there is a V output is there. Now, what is my V input? V input is 0, 5 volt and then 0. So my input is 0, then 5 volt and then 0. 0 volt, 5 volt and then 0 volt. This is 0 second and this is some 20 millisecond, right? Whatever it is. Yeah, 20 millisecond. But what they are asking a t equals to 0 plus only. That means this is not a matter of concern for me. They are asking only at t equals to 0 plus, no? So that is not a matter of concern for me. So now what will happen at t equals to 0 plus? So the scenario is, what is the initial voltage across the capacitor? 0 volt. Now what you have done? You have directly applied 5 volt. Initially there was 0 volt, nothing was there. Suddenly you have applied 5 volt. So will the capacitor change its voltage instantaneously? No. So what will happen? Whatever the voltage that you have applied, capacitor is having 0 voltage, whatever the voltage that you have applied here, that will be completely exposed to this particular terminal. 5 volt you applied, capacitor was having 0 volt, so 5 volt directly came to this particular terminal. Now what is the scenario? At t equals to 0 plus I am talking about, at t equals to 0 plus. So at t equals to 0 plus, the scenario is, this is minus, this is plus. At this node you are having 5 volt, at this node you are having ground. What will be your output? Now it will simply behave as a comparator. Now this has become a comparator. What will be your output? Sir, output will be negative potential is, negative terminal is having more potential, positive terminal is having lesser potential, output will be saturated to negative voltage. That's it. This is the scenario at t equals to 0 plus. So your output at t equals to 0 plus will be minus 12 volt. Every place this question was solved absolutely wrong till this date, everywhere. Now this year some gods have improved, some god educator, they have improved this year. Some gods are yet to improve. So for them I have already made this particular video that please improve. What I have seen is that what they would do, there is a negative feedback involved. They will say there is a negative feedback involved, so virtual short will be valid. Absolutely baseless statement. How there is a negative feedback? What is the first condition of negative feedback? That this potential should not be fixed. But just as I applied 5 volt here, the potential is fixed. So how there is a negative feedback involved? No, negative feedback is not involved. Not involved. Negative feedback is not involved. Directly your output is coming out to be minus 12 volt. Now what other people did, because they had to match the answer, no? They had to match the answer. So how they matched the answer? They started doing the frequency domain analysis. So here, this is capacitor and this is resistance R. So virtual short is valid. So what they did, V naught by V in they have written as V naught as by V in S. V naught as by V in S. This resistance which is R divided by 1 upon CS. So what you are getting? Minus RCS. So this is your transfer function V naught S by V in S, right? Then what they are saying is that, sir, I will take this V in S here minus RCS into V in S, right? Then they would say that, sir, S into V in S. In the time domain, if I represent d by dt V in T. Okay, this is the relation we are getting. Now, what is the input waveform that is given? This is the input waveform that is given, right? So, input waveform will be simply differentiated. Input waveform will be simply differentiated. So, here there will be a positive impulse you will be getting, and here there will be a negative impulse you will be getting. Now, you are getting a positive impulse. What you are getting? You are getting a positive impulse. Impulse means infinite amplitude, right? If it and there infinite amplitude means very large amplitude, but there is a negative sign. So, what will happen is that this will become negative. Like basically here there is a positive impulse, but there is a negative sign, so this will become negative impulse, this will become positive impulse. If there is very infinite amplitude means it will be saturated to minus 12 volt. Absolutely baseless explanation. We should be ashamed if we are giving this kind of explanation. Sir, like we have studied this particular thing, no? Yeah, these kind of things are written in the textbook as well. So what is wrong there? There is nothing wrong. But from here to here, what you are doing here, that is wrong. Like this is the frequency domain analysis, that is absolutely fine. V naught of j omega divided by V in of j omega, that is coming out to be minus j omega RC. Till this point, absolutely fine it is. Now you have to do the frequency domain analysis. This is your step function. So how much frequency content you are having here? If I say this is a sinusoid, this is a sinusoid I am having. This sinusoid is having a frequency of omega 1. If I make the sinusoid a bit more faster, somewhat like this, so what frequency it will have? It is having frequency omega 2, but it will be greater than omega 1. If I make it more faster, somewhat like this, it will also have some frequency omega 3, which will be much greater than omega 2. It will be much greater than omega 1. So here there is a very smooth transition. No? Your input is changing from 0 to 5 volt very smoothly. Here your input is changing from 0 to 5 volt a bit faster. Here your input is changing from 0 to 5 volt very fastly. If I make it step, something like this, that means input is changing from 0 to 5 very fastly. What does that mean? Here the frequency content only at t equals to 0 plus, that will be much larger than anything. So can I take, ideally it is infinity frequency content? Can I say in that manner? Okay, and the detailed explanation of this particular thing I have given in Fourier transform. Okay, that why you can take infinite frequency content here, why you can take zero frequency content here, and in between what kind of frequency content you can take, that has been given in Fourier transform. Okay, but people only teach analog and a few subjects, they wouldn't know what is the meaning of frequency content. So ideally I can say that, sir, this frequency content is infinity at t equals to 0 plus. So at t equals to 0 plus, what I can say, sir, this will be my V naught j omega. This will be a infinite frequency content, and this is my V of j omega. So eventually, sir, your V naught of j omega is coming out to be minus infinity. So in the time domain as well, sir, it will be coming out to be V naught. Basically, your output is tending to minus infinity. It can never tend to minus infinity. That means it will have to saturate at minus 12 volt. So this is how you need to do the frequency domain analysis. You are just matching the answer here, and this will not be the output waveform. Output waveform will be very interesting. Okay, it will go somewhat like this. And you can make this particular waveform as well. It will be much more interesting. Like I don't remember the exact waveform, but the full analysis for 20 millisecond everywhere. Like this is just at 0 plus second we have done, no? You can do the analysis at 20 millisecond as well. So full complete analysis from 0 to 20 millisecond. This analysis has been given in this particular video. Must watch this video. Must watch. Your concepts will be like, you will feel like that, sir, we are studying analog. For the first time you will feel like that, sir, yes, we are studying electronics. So please do watch this particular video. Here I have just given that at t equals to 0 plus what is happening. If someone wants to do the analysis in frequency domain, then he can do the analysis in this manner. But if he needs to do the analysis from 0 to infinity, so next time what they would do, the IITs will frame the same question, but they will ask the answer at 25 milliseconds. What you would do then? Differentiation? Saturate? Absolutely baseless. Okay? So they can ask the analysis at 25 milliseconds anywhere, like in between they can ask at 10 milliseconds. What you will say now? At 10 milliseconds, what you will do? So you see this particular video, here I have explained a lot of detailed concept. In this video only we cannot explain. No, like you would say that, sir, why you are recommending a lot of videos? Because in one video I cannot make it all. Already I have given it. Okay, so you watch it from here. And I am glad that a lot of good educators who used to claim that they are good and I am nothing, like I am just a 23 or 24-year guy who will teach what they have admitted their mistake and they have improved the solution. Okay, I have seen that people have improved the solution here. A lot of solutions also they have improved. So especially like I'm very thankful to them that now students would be learning something good, because from them more people would be studying, from me lesser people would be studying. That's certain, because they are at the higher platform, right? The platform which is having more audience. But here lesser people will be there. People are studying more from them, so that means they should improve themselves in a better manner. So I am glad that they are teaching the right things. They have they have finally understood their mistake, because from 2 to 3 years I am saying that, sir, please improve. Now finally they have improved. A few educators are still on their own ego. They are yet to improve. They should also improve. So if you are someone in touch with some good educator who feels like that, yes, we teach something out of the box, then send them these videos. That, sir, please try to improve. Okay, and surely one day they will surely improve. Let's go to the next one. Yeah, this is very simple question. Okay, like standard question it is. I will not say very simple, standard it is. So in these kind of oscillator problems where they are asking frequency of sustained oscillation, what you need to do? You need to pick any two nodes in the circuit. Any two nodes you can pick. Any two nodes. Let's just say I pick this particular node. This is the output of op-amp. So I am calling this as V1. Now other node also I need to pick. Let's just say I have picked the other node here. This is my V2. So now my target would be that I write down, first I will write down V2 by V1. V2 by V1. And the other target would be to write down V1 by V2. So I need to go from V1 to V2 and then from V2 to V1. I need to write down both of the gain. Let's just say this gain I am calling as A and this gain I am calling as beta. So then I need to multiply both of the gains. What I will get? A beta. Now the magnitude of A beta should be equals to 1 and the angle of A beta should be equals to 0 degree. This is the target. Then you will get the sustained oscillation. Okay. Why this happens? This is a bar question criteria. Why this bar question take place? All these things we can understand in comprehensive course. All these things we can understand in comprehensive course. But as of now, you just need to remember the results. So any two nodes you can pick. Now just let me know, is it very easy to go from V2 to V1 or V1 to V2? Like which will be the easiest path? If I assume my V2 here, if I say this is my V2 node, this V2 node, this will also be V2 node. So sir, directly from here to here I can write down the gain. From V2 to V1, can you write down the gain? Simple op-amp based gain. This will be V2. How much current this will drive? V2 by R. Or you can simply say that, sir, it is non-inverting amplifier. So this will drive V2 by R current, then this same current will be flowing here. So how much will be the drop here? So the drop will be V2 by R into R1. Right? So what will be your V1? Sir, V1 will be nothing but V2 plus V2 by R into R1. Right? So what will be the value of V1 by V2 you will be getting? V1 by V2 we are getting as 1 plus R1 by R. Or you can simply say that, sir, this was nothing but a non-inverting amplifier. The gain would be 1 plus RF by R, 1 plus R1 by R. This would be the gain. So V1 by V2, if I assume my V2 here, then it is much easy for me. So V1 by V2 I have already, sorry, V2 by V1 I have already find out. Not V1 by V2. Ahi, kya kar raha hu main? This is V2, no? Yeah, V1 by V2 I have find out. Yeah, V1 by V2 I have find out. So let's call this as A, this as beta. Like you can call anything, anyone. Doesn't matter. Let's call this as A, this as beta. Okay. So A value I have find out. Now I need to find out beta. So I need to go from here to here. So now what is my analysis? My analysis says that this is your capacitor C. This is your resistance R. Then this is your again resistance R. And this is your capacitor C. This is your V1 and this is your V2. This is C, this is R, this is R, this is C. You need to find out V2 by V1. Basic network analysis it is. What someone would do that he would assume Vx potential here, then he will write down the equation Vx minus V1 divided by, then he will find out the Vx potential, then he would know that if I know the value of Vx potential, then what is V2? V2 is nothing but 1 by Cs upon 1 by Cs plus R into Vx. So from there he will get the value of, then V2 will be there in terms of V1 and V2, then from there he can get the value of V2 by V1. So simple network analysis it is. How good you are with network analysis, that will be tested. So you need to find out the value of V2 by V1. I will not find out this Vx. What I would do is that here I will find out the Thevenin equivalent. Thevenin equivalent I am going to find out here. What I would do? Looking from here, how much resistance I am getting? Sir, R parallel with 1 by CS. Because input will be shorted, so R parallel with 1 by CS, what that would be? R upon RCS plus 1. And looking from here, how much voltage drop I will be getting? Let's just say I'm finding the VTH here. So what will be the VTH? So VTH would come out to be, Thevenin voltage is the open circuit voltage. That means this will not drive any current. So that would come out to be, sir, R upon RCS upon RCS plus 1. That would be simply R upon R plus 1 by CS into V1. So the CS would go here, RCS upon RCS plus 1 into V1. Okay. So the scenario is you have got the VTH as well, you have got the RTH as well. So VTH, RTH you are having. So the resistance that I am getting is nothing but RCS upon, sorry, not RCS, R upon RCS plus 1. R upon RCS plus 1. This is your VTH potential, which is nothing but RCS upon RCS plus 1 into V1. Then what you are having? You are having another resistance which is R, and then you are having another capacitor which is C. This is your V2 node. Okay, now we need to find out V2 by V1. We need to find out. So can we do this? Very easily we can do this. What is your V2? V2 by this particular potential. Let's call this particular potential as VTH. So what will be your V2 by VTH? Sir, V2 by VTH would be nothing but 1 by CS upon 1 by CS plus this resistance, which is R upon R plus R upon RCS plus 1. Say yes or no. Is that understandable to you? Right? Calculation it is, there has to be some calculation. We cannot do anything about it. So when we solve it, what we are going to get? This RCS upon this RCS plus 1 goes up upper side. The CS would also be there. Like what I am doing is that here what I would do, this is simply mathematics now. What you would do is that I will take CS RCS plus 1 as common. Not common, sorry, like what do we call it? LCM I will take. CS into RCS plus 1. LCM I will take. This would become RCS plus 1. Then this would become RCS upon RCS plus 1. So RCS square plus RCS and then RCS you are getting. So here RCS square plus 3 RCS plus 1 and then this goes upward. So what you are getting? RCS plus 1 RCS plus 1 upon RCS plus 1 upon RCS square plus 3 RCS plus 1. This is your V2. Now multiply with VTH. What will be the value of VTH here? VTH is RCS upon RCS plus 1 into V1. This is the value of V2 you are getting. Now V2 by V1 is very easy for you. V2 by V1 is nothing but this and will get cancelled out. What you are getting? RCS upon RCS square plus 3 RCS plus 1. Okay, so let's go to the omega domain now. J omega RC upon 1 minus this will become omega square R square C square plus 3j omega RC. So what do you see now? Sir, I am getting V1 by V2 as 1 plus R1 by R. This was the scenario. 1 plus R1 by R, V1 by V2. And sir, I am getting V2 by V1 as j omega RC upon 1 minus omega square R square C square plus 3j omega RC. Right? Now what you need, let's call this as A and this as beta. So the first condition that I need is angle of A beta should be equal to 0 degree. Can I write down this as in this manner? Angle of A plus angle of beta should be equal to 0 degree. How much angle this is providing? 1 plus R1 by R. This will be a constant value. R1 will be a constant value, R will be a constant value. That means it is having no phase. What is the angle of A? What is the angle of A? That is 0 degree. That means how much angle you would be expecting from B as well? You need 0 degree angle. If you need 0 degree angle, that means what I will do is that I will find out its angle and then put it equal to 0. But just think about it, have some patience and just think about it, that if this particular thing goes to 0, 1 minus omega square R square C square goes to 0, then what will happen? If this thing goes to 0, then V2 by V1 would become j omega RC divided by 3j omega RC. then this and this will get cancelled out. It will become simply 1 by 3. How much angle it is providing? How much angle it is providing? 0 degree. That means if I put this equals to 0, then my job would be done, right? 0 degree angle I will get. So from here what I am getting is that if you find out the value, omega value is coming out to be 1 by RC, because omega square r square c square would be 1. So omega value is coming out to be 1 by RC. So frequency of oscillation is 1 by RC. This is the first condition we are getting. Frequency of oscillation is 1 by RC. Now when the frequency of oscillation is 1 by RC, then what was the value of beta? Value of beta you have got to be 1 by 3. This you have got at frequency of oscillations, which is 1 by RC. Now another thing you know that I need A into beta should be equals to 1. Two condition I said. A into beta, mode of A into beta should be equals to 1 and angle of A beta should be equals to 0. So this should be equals to 1. 1 plus R2 by R1, R1 by R, this is your A. And what is your beta? Beta is 1 by 3. That should be equals to 1. That means this value should be equals to 3. 1 plus R1 by R should be equals to 3. So from there R1 is coming out to be 2R. There you go. That's the answer. So complete concept of oscillator I have taught here. This is how you analyze any oscillator. Okay, so what is the answer? 2R and 1 by 2 pi RC. So this is the complete concept of oscillator. This is how you analyze the oscillator. Take any two nodes, but choose the node smartly. It's not that sir this is V1, this is V2, then it would be very complex. From V2 to V1 very easily I can go. From V1 to V2 I have to put some effort. So only one time I will put the effort. If I had to use this as V2, then both of the times I would have to put the effort. But only once I will put the effort, and you can see that in that manner I will find out the value of V1 by V2, V2 by V2, V2 by V1 and V1 by V2. This is A, this is beta. It should provide me 0 degree gain. Sorry, it should provide me 0 degree phase shift. This is also giving me 0 degree phase shift. Job done here. Gain should be equals to 1. That job is also done. So this is how I will get this particular question. This is how I will get it correct. All good? So answer is B. Let's go to the next one. Diode circuit. So I thought that one question I should take on diode circuit. Why I took this particular question? Because I need to teach you one concept, or you can call it trick as well. What is the trick? Like if I give you this particular diode circuit, here I am saying V1 potential, here I am saying V2 potential, and I am saying that cut-in voltage is 0. Just as I say cut-in voltage is 0, you will be very happy. You will say that sir, if V1 is greater than V2, then diode is on. And sir, if your V1 is less than V2, then sir, diode would be off. Right? But if I give you the same scenario, same circuitry again, V1, V2, now I am saying that your cut-in voltage is 0.7 volt. So now you will be not that much happy, no? What you will say? That sir, V1 should be greater than V2 plus 0.7. Then diode would be on. But here you need to think something, because cut-in voltage is 0.7. So V1 should be greater along with that 0.7 greater. Then it would be on, otherwise it would be off. So here you have to think, right? Now I am doing something. Whenever cut-in voltage is given, what you should do? Whenever cut-in voltage is given, always take out the cut-in voltage. Always take out the battery equivalent to cut-in voltage out of the diode. What I am saying is that this was the diode I was having. What is the cut-in voltage? 0.7. So this is your P node and this is your N node. This is your positive, this is your negative. So in the same direction, I will make a battery, and this battery will have a potential equivalent to cut-in voltage. So my diode, this diode has been replaced by this particular diode. Now this potential was V2, this potential was V1. Now this diode is having 0 cut-in voltage. Can we get the same condition? Yes. If this is V2, what this would be? V2 plus 0.7. What will be the potential of this node? That would be V2 plus 0.7. And here what is the potential? Here that is V1. Now if V1 is greater than V2 plus 0.7, what will be the scenario? Diode is on. Like as of now, you might feel like that, sir, this was easier. Like I could think. But in the examination, if here only the two diode circuits are there, if multiple diode circuits are there, then what would happen? You will again and again think. No. What you would do is that you will take out the battery out of the diode. That's it. Take the battery out of the diode. If this is the scenario, how would you take out the battery? If this is the scenario, how would you take out the battery? It is having the cut-in voltage of 0.7 volt. This is your V1, this is your V2. Without even thinking, I need to tell when the diode would be on. What I would do? sir, take out the battery. That means this is my V1 only. This is my negative, other one is positive. So in which direction I will take? Negative, positive. In this direction I would take. And then diode as it is. And this node, this potential is V2. This is my diode. Battery I have taken out 0.7 volt. So what will be this potential? This potential would become V1 plus 0.7 volt. So what you can say? Now it is having cut-in voltage of 0. So what you can say that if your V2 is greater than V1 plus 0.7, if my P potential is greater than the N potential, then my diode would be on. So is that trick or whatever you can call it, is that clear to you? That here, sir, I would have to think much, but here no thinking I need to do. So from the diode, I will simply take out the battery. So from the diode, simply take out the battery. This is your V in. So how I will make this circuitry in the examination? So this is my diode. Simply take out the battery from it. This would be the battery, and this is the scenario you are getting. Again, take out the battery. Like, sir, battery should be made here or it should be made before that, doesn't matter. Both are in series. This diode and battery both are in series. You can make anywhere. So the battery would look, this is downward, this is upward. And this is your V out. Then there is this 1 kilo ohm resistance, and then there is this 1 volt. 1 kilo ohm resistance, 1 volt. This would be the circuit, and both are having a cut-in voltage of 0.7 volt, 0.7 volt. Now, sir, I need to make the characteristics. Sir, I will make the characteristics and match the option. This would be a long task. Whenever the characteristics question is coming in the examination, what you would do? First, you would see the options. Do you need to analyze it completely? See the options, no? Try finding out that value of V in. Try finding out that value of V in where there is different V naught in all the 4 options. What I mean to say is that if I say V in equals to 1.7 volt, at 1.7 volt, this is giving me output 1 volt. Here, this is giving me output, I don't even know what will be the output. I will have to get the answer. Because at 1.7 slope is 1, so it will also giving me the output 1 volt. This is also giving me the output of 1 volt, and this is giving me the output of 0 volt. So here, if I check V in equals to 1.7 volt, what is the output I am getting, then only one option I will be able to cancel out. But I need to check that value of V in where we are having different output at all the points. So let's see at V in equals to 0. At V in equals to 0. What is the output you are getting here? 0 volt. What is the output you are getting here? 1 volt. And what is the output you are getting here? Some negative potential. At 0 volt, some negative potential you are getting, right? And here some positive potential you are getting. What is the potential you are getting? That I don't know. Look, here perfect 1 volt you are getting. Here, sir, somewhat lesser than 0. Sir, here somewhat lesser than 1. And here, sir, perfect 0 I am getting. Here perfect 1 I am getting. That means when V in is equals to 1 volt, in all the 4 options you are getting different output. So what I would do, I would simply put V in equals to 0 volt and analyze it. Whatever the output you are getting, based on that I will click on the option. That's it. Is that clear to you? So if 4 characteristics are given, why would you check at all the points? Why would you make the characteristics? These kind of question you have solved in your class notes, that is fine. But in the examination, you need to do it quickly. So check that value of V in where different outputs are there. So when V in equals to 0 volt, my job would be done. Now when V in equals to 0 volt, what you would do? You would apply the open circuit test. How would you apply the open circuit test? I will just simply copy the same circuit and I will apply the open circuit test. Applying the open circuit test here, what I would do is that I would make it open circuited. I would make it open circuited. This was N here, this was P, and I would make this as open circuited as well. This was P here and this was N, right? Now I know that cut-in voltage is 0. What is the scenario here? So this is 0 volt. Here also there will not be any current. So this potential will be 1 volt. 1 volt, this potential will become 0.3 volt. 1 minus 0.3, 1 plus 0.7. Sorry guys, very big blunder it is. 1 plus 0.7, this potential would become 1.7 volt, and 1 minus 0.7, this potential would become 0.3 volt. At N you are having 0 voltage here, and at P you are having 0 voltage here. So which one will turn on? P 0, N at 1.7. N is at 0, P is at 0.3. Which will turn on? This will turn on. What does that mean? that means this path would turn on now. This particular path would turn on. If this path is turning on, then what will be the scenario? This path will be gone, this path is gone, the upper path is gone now. So this is how my circuit would look like. Vin equals to 0, and this is how the circuit would look like. Now this is 0, so this potential will also be 0. Let's remove all this path. This potential is 0, this potential will also be 0. So what this potential will be? This potential will be 0.7 volt. That means your V out is coming out to be 0.7 volt. In which of the option you can get 0.7 volt? 0 volt wrong, 1 volt wrong, some negative value wrong. What does that mean? Answer is A. So in the examination, in maximum 2 minutes, I will be able to solve this question. 20 seconds I will take to read the question. Then what I would see? Diode is there. Vin equals to 0 volt. Different answer I am getting. Take out the battery. This diode will be turning off. This diode will be turning on. If it is turning on, it will be replaced with the battery. 0 plus 0.7 output will be 0.7. Option A correct. Is that understandable? Okay. So I hope now you have a clear idea of diode circuits as well. So we have discussed a lot of problems. Let's end this video here. We have discussed 10 questions, I guess. 10 questions we have discussed, and now I hope you are much better person in analog. So now what I expect from your end, you comment down that what did you feel. If you felt very good, we can bring these kind of videos for other subjects as well. For communication, I have brought some questions. From signal system, I have brought some questions. Last year, I have brought everything for digital electronics. I can bring it for more core subjects like for EDC, for EMFT, right? You struggle here. I don't think you would be struggling in network analysis. I hope network analysis is clear to you. So network analysis, I don't think I require it. Along with that, we are framing full length question paper as well. They are very high quality question paper. So there also you would get a lot of questions, and we are making video solution as well. So that also you can attempt. Okay. Control systems, Anish sir has already put. Mathematics, Anish sir has already put. In aptitude, I have already given the solutions of all the PYQs. So all the subjects are in command now, right? You are like more than enough content we have provided. Right from the beginning, we are providing the content, and I hope now you are feeling much better in your preparation. After watching this video of analog, you are much better in your preparation. And whatever the videos that I told you to watch, that you should be watching, and whatever the content that we are bringing here, that also you should watch. Now let's do the course promotion. So I will put a course promotion video, and this video has ended here. Okay then, yeah. Thank you very much. Happy learning. Please comment down. Please comment down. Okay.